Good morning, everyone, and welcome to FOSDEM. I'm Jeremy Bennett. I'm Chief Executive of Embench, but I am an engineer by profession, and this is an engineering talk. Just if you're wondering why I'm looking like a 1960s civil servant out of an Ealing comedy, I'm part of Open UK, which is the trade body for open source businesses in the UK. It has got a new lease of life with a new chief executive, and you'll see they've got a stand downstairs and they're all wearing hats like this, and so I'm advertising it. It is boiling hot. I'm going to take it off now. Actually, there we are. So that's a little less formal. So the subject of this talk is about using benchmarks to improve compilers. Our day job, what Embench does, is we develop LLVM and GCC compilers. If you've got a new processor chip you're bringing out, we're probably the company you come to help you bring up GCC, LLVM, and all the tools around it. I have been involved with the Embench project for the last year or so. I'll tell you a bit more about that. And then this is more of a talk about a process. I'm not magically going to tell you all the secret tricks for improving a compiler, but I'm going to tell you how you can find out what those are. So, first of all, about Embench. The first version of Embench will be launched at Embedded World later this month. It's Embench 0.5 because we still consider it our first sort of experimental version, and it's a free and open source set of benchmark programs for benchmarking computers. Let me tell you a bit more about it. We've tried to benchmark computers going a long way back, 1972 and Whetstone. How many people here have ever run Whetstone? How many people here were born before Whetstone was written? Yeah, okay. Then we've got LINPACK. LINPACK is still used. It's the basis of the top 500 supercomputers, but it was written in 1977. Drystone came along, inspired by Whetstone. It's the first general synthetic benchmark for running on systems and evaluating how a general computer works. And then you get the industry consortium, the SPEC consortium, forming to actually try and say a single program isn't enough, let's have a set of programs. And that's an industry consortium, very well respected. Downside is you have to pay to play. It's not freely available. And you find CoreMark, that came out of Embassy, and I'll say a bit more about Embassy in a moment, but CoreMark is what everyone quotes, and I've just been told the RISC-V dev room downstairs has just been quoting CoreMark as the performance of the low-risk platform. And the problem is CoreMark is like Drystone. It's a new Drystone, it's a synthetic benchmark, it's a single program. And it has done one thing, it has improved the abilities of compilers to optimize CoreMark. Okay, and then others, another mainstream one, MLPerf, you may have seen it in EE Times last week. That's a new benchmark suite for measuring the performance of machine learning systems, very much for the AI world. And there is a connection which I shall come to in a moment. And then there are some others that are less well known. The top row is the well-known ones. There's Embassy. Well, Embassy is reasonably well known in the embedded space. It's a set of embedded benchmarks. Again, it's pay to play. It's a consortium. It's not free and available, but they're quite widely used over time. When we get to the free and open source world, you've got MyBench. And MyBench has been around for, what, 20 years nearly. And that's a set of small programs you can use for evaluating systems, widely used in academia because it's freely available. We did some work on energy efficiency. Some of you may have come to the dev room 5 years ago here, looking at how compilers could influence energy efficiency on embedded systems. We needed a set of benchmarks for embedded systems. That means they don't use printf. They don't use libraries very much. And that's the Bristol Embench Embedded Benchmark Suite, or BEEBS. And actually, BEEBS isn't new because it builds on MyBench and one or two other benchmark suites there. And lastly, you've got the timing analysis benchmark, TackleBench, which came out only a couple of years ago. And not many people have heard that, but it's a good set of programs. And in fact, TackleBench builds on previous benchmark suites as well. So we came to the conclusion that there was nothing perfect for general use. Okay, so we decided to create a new benchmark suite. It's called Embench. And we drew 7 lessons from all those existing benchmarks. So first of all, it's got to be free. Okay, if you don't make it free, Spec and Embench, and why does everyone use CoreMark and not its parent lot, Embassy? Because CoreMark is free and Embassy is not. Even though Embassy, being a set of programs, is a better option. It must be easy to port and run. If it's a pain to bring it up, then people won't use it. It must be real programs. The problem with synthetic benchmarks is they try and capture a bit of everything and end up being a bit of nothing. And so we wanted to build a benchmark suite built on real programs like Spec and Embassy do. You look at some of those benchmark suites, Drystone, there isn't an organisation to maintain it. It's the same forever and forever. So you need a supporting organisation to maintain it. But people still want things simplified. They want a single number, so you need a summarising score. You need to be able to say, this is my Embench score. There's all sorts of ways you can summarise. We came to the conclusion that actually benchmark suites can be dominated by one big program or one fast program. Geometric means actually help to level that out. And using the standard deviation means you can see the variability. So you can see if one program is dominating the impacts. The other thing we do is we make the data relative. Instead of saying we've done the geometric of all these program sizes, if we're measuring code size, we'll take it relative to a particular baseline value. And lastly, we see on those benchmark suites, there are some that are purely academic, like TackleBench, like MyBench, and they're not heavily used in industry. We find things like Embassy and SpecMark, they're done by industry, but no one uses them widely because they're all paid for, they're teams pay for, and they're focused just on industry's needs. And CoreMark is free and was developed by industry, but actually hasn't had the input of academic latest thinking. So we wanted to involve both academia and industry. So what was the plan? So we started the first 6 months of last year, a small 4 of us, Dave Patterson, and Dave Patterson is the originator of Risk 1 and the originator of Risk 5, Professor Emeritus now at Berkeley, and he drove that, and that's the connection to MLPerf because he also was behind MLPerf. I came in, and the reason I came in is my involvement with Beebs, and Embench is derived from Beebs. Palmer Dabelt came in because the Risk 5 community were very interested in this. At the time he was at Sci5, he's now at Google. And Cesare Garlatti came in because it's not all about compute speed. Cesare is very much looking at how fast things react, what are context switch times, what are interrupt handling times. So it's more than just compute times. And for 6 months we met every month in California, in Sci5's offices. And in June we announced this project to the wider world and opened a wider group. And there is now a group, if you go to embench.org, you can join the mailing list, you can join the monthly calls, there's a Git repository with all this on. Okay, if you go to embench.org, you can find all the links there. And the goal is to launch, at the end of this month at Embedded World, a first version that is reasonably stable and that people can try. But it is only a first version because one of the things that came from our principles is you've got to keep this alive. Embench in 2 years' time will be a different set of programs because we don't want all the compilers to be improved to our set of programs and then they're just good at optimizing that set of programs. We're going to keep on changing them. That's what SpecMark's done, it's what Embassy's done. Okay. It's currently, we tried not to do everything at once because otherwise you won't succeed. So we've focused initially just on the small IoT class device, 64K RAM, ROM, and we've got 19 benchmarks which are small program kernels, real program kernels aimed at deeply embedded computing. We'd like a couple more. I think we're running out of time for 0.5. We'd like to get Bluetooth LE represented in there. We'd like elliptic curve DSA. It's quite hard to find an elliptic curve DSA system that's real that will fit in that size program. Okay? So we also have an early version of a context switching benchmark. So that's that thing that Cesare is interested in. We really would like more help with that. That's not going to be, that's going to be a just an exemplar. That has to be written in assembler. It's not a program you just compile and run. It's a description of how you write an assembler program to measure this on your platform. Okay. At this stage, we've got simple Python build and run scripts, and that's where the last minute panic work is being done at the moment, is to get that clean and easy to use, ready for 3 weeks' time. So far, most of the testing has actually been with Verilator models and simulators. The latest work is starting to actually get it working on real hardware, because it's no use if you can't run it on real hardware. And for deeply embedded systems, that's not quite as easy as it is for something running Linux. Okay? So we're widening it. You'll see me talking about ARM and RISC-V today, because I want to do comparative stuff, but we've done it on ARC, we've done it on Atmel AVR, and we'll do it on more as we go forward. So we've got a benchmark suite. Here it is. Here are the 19 programs. None of these are new. We've taken them from other people. Okay, they're free and open. It's GPL3 licensed. You can see they're hundreds or a small number of thousands of lines of code. They're hundreds, or I think the biggest, 10 kilobytes of code and data size, and code size, data size, and they've all been normalized to sit in a loop, so they all take about 4 seconds to run on any platform, and there is a parameter to control that. The other thing is they're tried to be a mix, and this is something that came from Beebs. So we looked at what the proportion of branching programs, memory access was on ALU in the programs, and you can see here some of them have got lots of branches, some of them have got very few branches, some have got lots of arithmetic, some have got few, some have got a lot of memory, some have got few. There's no floating point in here. One of the things we also said, let's just do an integer one to start with, we'll worry about floating point. Well, there's almost no floating point. You can't have real programs with a little bit of floating point, but we've thrown out the explicitly floating point ones. So that's the benchmark suite. I say, please join in. It is a community effort. There is no one paying for it other than people giving up their time. The group is chaired by Dave Patterson, so it's a good chance to get to know Dave if you want to talk to one of our great computer scientists. I'm the vice chair, so I'm the one who makes sure all the meetings happen and so forth. This is not really a talk about Embench. I just wanted you to know about it because this is a talk about compiler optimization. So what affects Embench, or indeed any benchmark results? Well, the instruction set architecture. How good is your architecture? Is it ARM or RISC-V or ARC or AVR? Okay. What extensions are you using? Is it the ARM v7 or the v8 architecture? Are you using Thumb2? Are you using RV32? Which set of extensions, MCB, whatever? Okay. What compiler are you using? One of the open ones like GCC or Clang LLVM, or a proprietary one like IAR. Okay. And which optimizations you're including. So you're using the compiler, but how much optimization have you turned on? Are you optimizing for size? Are you optimizing for speed? Okay. Okay. And you might think that you've got a brand new architecture come out, its compiler might be immature. And if you've got an old architecture, its compiler might be mature. So today I'm going to look at ARM and RISC-V. RISC-V quite new, ARM been around for a while. The other thing that can affect things is the libraries. And I'm not going to talk about libraries today, but you can make your programs as good as you like. But if your libraries they rely on, and even embedded systems rely on libraries for things like emulation and so forth of floating point, however much you rely on that, you're going to have some library code in there. So Embench at the moment, and this is still a bit of a debate, excludes libraries when sizing, because actually even the little emulation libraries, the C runtime startup, for those smaller programs, they can completely dominate the code size, less so the performance. Okay, and we don't want to keep on measuring the same thing again. So if I want to use it for a compiler, let's have a comparison matrix, because what I want to do is learn from other people. Just as the previous talk, you got the question about LLVM and LLDB and GDB, you can learn from each other. So let's look in 2 dimensions. What can we learn by comparing Clang LLVM with GCC for a particular architecture? And secondly, what can we learn by comparing Clang LLVM for different architectures? What does Clang LLVM do well on one architecture and on another? And the idea here is to share knowledge, to learn from others. So at the gross level, we can actually look at two compilers. So here's RISC-V LLVM against RISC-V GCC. I've looked at code size, I've looked at the various optimization levels and what it does to code size. So you can see here that as we increase optimization, code gets bigger. Okay? And notice that they're all normalized to a reference platform. The reference platform happens to be the code size of RISC-V IMC run with -OS using GCC 9. Okay? That's actually going to change for the release. The reference base architecture will be Cortex M4, but I'm using what we've got today. And you can see there are little bars. Those bars are the geometric, a single geometric standard deviation up and down. Okay, and you can see that, you know, this is close to the reference. Okay, so this is the reference for size OS. Okay, and the error bars are quite small. Up this end, they're quite big. Okay, and we can also look at code speed. So Embench doesn't actually say what the metric is for. You can do it for code size, you can do it for code speed. We haven't done it yet, but in principle, you could do it for energy efficiency. Okay? And if we look at code speed, what we find here is that obviously when you go for small code, things go a bit slower. When you go for high optimization, things go a bit faster. This time it's normalized against RISC-V 32IMC with -02 and GCC 9. Okay? Perhaps surprising for RISC-V, you don't get a huge amount of speed up. Optimization's not perhaps as effective as you might hope. So we can do that gross comparison. That's just to give us a big picture. And we can look by architecture. For architecture, I'm going to focus on code size. The reason for that is I haven't actually got good, reliable measurements of ARM execution speed. And because I'm focusing on embedded, I'm going to focus for the moment on the rest of this talk on optimization for code size. The same analysis applies to optimization for code speed. It's just I've only got a 40-minute slot. Okay? So code size by architecture. So yellow for ARM. And here you see that ARM is a more mature compiler. When you optimize for size, it actually does better than RISC-V. More mature architecture, I'm moving more. When you optimize for speed, actually ARM's code size goes out the window. But that's a bit because ARM is doing far more optimizations there. If I did have the performance figures, you'd actually see ARM gets much more of a speed up when you turn on -03. Okay, that's at the expense of doing a lot of a loop unrolling and inlining and so forth. So the code size gets bigger. That's exactly what you would expect to see. So far, so good, but it doesn't hugely help the compiler writer beyond being able to talk about how good my compiler is in the round. That's not what I'm interested in. So let's go down to the next level and let's look at individual benchmarks. Let's compare LLVM and GCC code size. This is for RISC-V. With -OS. So there's optimization for size. I've compared with -OS because GCC does not support -OZ. Okay. Now, you can see there, just visually, that some of the benchmarks, RISC-V has bigger code and LLVM has bigger code and GCC has smaller code, and for others it's the other way around. But it's a bit all over the place. It's much better if you sort those benchmarks by that's exactly the same data, but I've now sorted by the difference. So at the end, you've got a Harmont 64. And for that, LLVM, the geometric mean, the LLVM, the code size, there's no means here because this is individual benchmarks, is nearly twice as big as the code size that you get with GCC. So we could learn something by looking at that one. What is it with that particular benchmark that RISC-V does so dreadfully, that LLVM does so dreadfully when compared with GCC. Up the other end here, we can look at HuffBench and say there are some there where LLVM's getting it right. What's LLVM doing right about HuffBench that GCC isn't so good? And that helps both the GCC and the LLVM team. This is not who's got the better compiler, it's what can I learn from each other. And we can do the same analysis on ARM. Okay, and so you can see from ARM that there is the cubic program and the crypto programs ARM's code size is really good. If you want to write a small crypto program, choose ARM as your architecture, not RISC-V. That's the message there. But there are others here where they're solving the n-body problem and a state machine. Actually, the compiled code for RISC-V with LLVM is better than that for ARM. Okay, so we can look at both of those. And the ARM guys can look at that and see, well, what is it that the RISC-V compiler is getting right that ARM could learn from? So we're starting to get now and see there are some interesting programs there. So let's go deep. And this is where we start to get the useful information. There's a really good option to NM that sorts your symbols by size. So I've done NM size sort for the Clang and GCC compilations of the program with the biggest difference. Okay, and I've only shown the text size there. I've stripped out all the data results there because I'm not interested at the moment. I draw your attention to this. There appear to be 3 programs in the GCC image that are not, so 3 functions that are not in the Clang image. Those have clearly been inlined. And you can see that the benchmark body is hex 16E on GCC, and the benchmark body over there is 5C6. So it's much, much bigger, 3 times bigger on Clang LLVM. So let's delve in deeper. Well, if we look at the source code, mont64.c for this, we'll see that those famous functions, mul64, modulo 64, are called many times, partly from mul, but mostly in benchmark body. Okay? So if I am doing inlining, I'm going to put 3 copies of each of those into the benchmark body, which, given I'm optimizing for size, is possibly not such a good thing. The third one that went missing, the XGCD function, actually only appears once. Inlining something that only appears once is probably not a bad idea for code size. Okay, and we see that if we disassemble the benchmark body, because if you look in benchmark body, you see series of code sequences that become mul, hu, mul add, and that same sequence appears 3 times, which is the inlining 3 times of the function. Whereas those are the only muls you see at all in benchmark body and GCC, and they're nothing to do with those functions anyway. What that's telling us there is we can learn there's too much inlining going on, arguably, in LLVM for -OS. Now, there's a case to be made for saying, well, but I've got -OZ in LLVM, and maybe I'll turn it off in -OZ. But that's given you some insight that if you're worried that OS is perhaps not yielding what you want, you could perhaps look at inlining. And in fact, you can look at the debug information because there's a helpful DW tag inline subroutine to tell you when you've inlined something. And if we compare all the binaries, LLVM and GCC, we see that in general, that LLVM at -OS does far more inlining. So if we want to improve LLVM for RISC-V, one thing we could do is reduce the heuristics that control the amount of inlining going on. Okay? And I draw your attention to Pico JPEG. Now, Pico JPEG, I think, is 3rd in the list of ones with differences. And look at that. It's got 180 inline functions compared to 40 in GCC. Even GCC does some inlining here. But the point is, it's got that huge amount of inlining going on. It's not actually, it is only 3rd in the list. It's not top of the list. So there's more going on in code size than that. So we've done a bit more digging. And this can go on for ages and ages. And I'm not going to go on for ages and ages. So if we look at cubic -OS, which is one where the inlining is lesser. In fact, there's no inlining going on at all in cubic, but cubic is still worse between Clang and GCC. What we see is the main routine, solve cubic, is notably bigger on there. So that suggests looking at solve cubic would be an idea. Well, the first thing we notice is that the first line of solve cubic is to set up the stack. And on LLVM, I have a far, far bigger stack frame, 1,424 compared to 304 bytes on GCC. And the reason for that becomes clear. So that gives you a hint that what's the difference there? And you can see it here, which is where I've looked at one particular line of code and how it's translated. I've picked this out to illustrate it. We looked at the whole thing. But look at this. When I want to load a constant, LLVM explicitly loads a 32-bit constant by loading the upper immediate and then adding in the lower bits. GCC has a small data area where it puts those constants it wants, and it can do a single load. So 32 bits here, 64 bits needed here. Okay, so that's one of the reasons for code size. And there's an element you're going to end up saving stuff on stack, which is why the stack has got so big. Okay? And if you go and look and debug and look at the S data, a begin plus A8, they do have the constants in there that you would expect. So GCC is making aggressive uses of a small data section. That hasn't made it into LLVM yet. So there's an optimization we could add to Clang LLVM by looking at what GCC does. But we can also learn more from GCC, because actually the first two times that does, two 32-bit instructions to load two 32-bit constants. Those 32-bit constants are 0 and 0x4 0000000. Okay? And LLVM actually is intelligent. So yes, it uses small data, but it uses it mindlessly in GCC. LLVM doesn't use small data, but it's quite intelligent about constants it can do clever things with. So it knows that it can use a short instruction, c.li, just to load a 32-bit 0 value, and it knows it can actually only needs to load the upper bits to set that big constant there. So in this case, GCC used 64 bits. We only use 48 bits in Clang LLVM. So the GCC guys can learn something from Clang LLVM on that one. And the point of the benchmark suite is it gave you the pointers to find this. And that's why a benchmark suite is useful, and the analysis that goes with it. I'm going to finish now with just a passing comment, because you can do the same looking at ARM RISC-V. And very quickly, you see things like here, the ARM sort of augmented instructions, where you've got an exclusive OR of R2 and IP into R0, but you're allowed to actually rotate the second operand. So you've got these synthesized operands. That's really useful for cryptographic things. It gets heavy use in NetAES, the AES function. So what you do in 32 bits in ARM, you need a total of, if I've added that up right, 96 bits in RISC-V. Okay? And that structure comes up quite a lot in that cryptographic code. That's why ARM actually comes out well on the cryptographic stuff. That's something to bear in mind when looking at instruction set extensions for RISC-V. We can't do much about that in the compiler. That's an architectural thing. Okay? So sometimes the answer you'll get given is you can't fix this, but other times you do. We do observe other things. ARM makes heavy use of constant pools. We saw a bit of that in GCC. Okay, at the end of functions and having a global area with short accesses for global constants via other registers. Whereas RISC-V tends to have many global loads and stores. The other thing we see is ARM famously has conditional instructions. Those turn into explicit loops in RISC-V. So we can do something about constant pools because we can implement that in Clang LLVM. The other two are architectural. That's over to the chip designers to sort out. So I hope that was useful. I was exploring how you go around the day-to-day job of improving a compiler. So standard benchmarks provide a useful comparison tool, and comparison between different environments can identify optimization possibilities by comparing compilers, by comparing architectures. But some problems can't be fixed by the compiler, and it works for any benchmark set. I've chosen Embench because I've worked with Embench and it's being launched next month. It's a good chance to talk about it. And we use that professionally in our day-to-day job. But there are other benchmark suites out there. You can use any of the ones I talked earlier. There are others specifically compilers. And I particularly draw your attention to our colleagues from Western Digital and their repository of tiny code fragments that break compilers. Okay? And you can do exactly the same analysis. It's not a benchmark suite. It's a is your compiler any good suite. And that's a great set of code fragments to look at. But exactly the same analysis applies. It's the same technique. So thank you very much. That's my company address. And embench.org. I do encourage you to get involved with Embench. If it's going to succeed as a free and open benchmark suite, it needs many, many hands on it. And I should take questions, and I've already got one. Yes.
Hey, how we can get involved with Embench?
So the question is, how can you get involved with Embench? You go to the website, you sign up for the mailing list. It's a conventional listserv mailing list. One of the things that will get announced on that mailing list is the date and time of the monthly call, which is the third Monday of every month on at 8 a.m. California time, so 5 p.m. in Belgium. And that call is actually implemented using Zoom. I know the concerns over using Zoom. We can't get everything right, but okay. So that's how you get involved. And it's a repository, it's a GitHub repository. Send in your issues, send in your pull requests. And my next 3 weeks will be spent dealing with the queue of pull requests and issues that have been raised. And the more the merrier. Yeah. And it goes on. It's launched next month, but it's going to go on. It's going to be renewed year after year. So new benchmarks are always welcome.
Are you planning to version Embench? So, for example, like you've got spec 2K6, so even though you might be changing the programs, people can still get the historical data across a large field?
So the question is, are we going to version Embench? The answer is yes. Version 0.5 this year. The intention is to renew it every 2 years. I suspect the first full version of Embench will probably come out after only a year, because I think that'll be enough. And then every 2 years, and I've already got the first submission of a program for the net to go into the benchmark suite next time round. Actually, I'll take this one over here. Give it.
So you say you tested it on real hardware, yeah? But there are obviously differences between chips, because some might have, especially with Skype, some new ones might have speculative execution, some might not. So, so these benchmark numbers you showed for the performance. So, what's kind of the reference platform used there?
So the question is, what is the reference platform used for Embench? Because reference platforms are implemented by the hardware implementation. It is the RI5CY Risky core from the Pulp project at ETH Zurich, and that's an open implementation, and it is a specific commit from their GitHub repository of the Verilog source. Thank you.
Do you plan to separate the floating point test benchmarks from fixed point benchmarks? Because, yeah, that influence the numbers, final numbers.
So the question is, are we going to separate out floating point benchmarks? The answer is, the first benchmark suite is not called Embench, it's called Embench IoT. It's specifically IoT class integer. We see two directions going in the immediate. One is to do a floating point aimed at that same class of processor, because there are embedded floating point, and you can get M4 with floating point unit. You can have RV32 IF. So absolutely. And the second is, we also want to do benchmarks appropriate for application class processors. They're going to run on an x86 or an ARM-A class processor, AArch 64 type architecture. Those are projects for the future. We're looking for people who want to join in, take ownerships of those. So I would expect in the future there will be a series of repositories for the different classes of Embench, each versioned. Yes, you have John. Very good question from Jerome. Are those benchmark figures for speed numbers, or are they relative to the clock rate? And the answer is, we report both. Okay, the absolute value, tells you how fast your processor is. The value per megahertz tells you how efficiently you've implemented it. Okay, and we did do some figures with RISC-V comparing the risky core from ETH Zurich with an early Sci-5 core, and actually you found the risky core was about 5% more efficiently implemented. When you divided by the megahertz, it was the same. The speed data I gave you were from a very later model of the risky core, which I happened to clock at notionally 1 megahertz, so it was divided by 1, so the two figures are the same. Any more questions? Thank you very much. Perfect timing.